Hey everyone, welcome to our fourth lesson in our unit on kinetics and equilibrium. Our lesson today is going to be on reaction spontaneity. I know that's a mouthful there. And exactly what conditions will allow a reaction to be spontaneous or non-spontaneous. There's going to be a couple factors that contribute to that. We'll talk about what it actually means for a reaction to be spontaneous. So today you should be able to define entropy. And you should also be able to explain that systems in nature spontaneously undergo changes toward a state of lower energy and higher entropy. This is what we're going to use to help determine if a reaction is spontaneous or not. So spontaneous chemical changes are chemical reactions that proceed on their own once they've been initiated. So once we start a reaction, if it's spontaneous, it will continue from reactant to product until everything has been used up. All reactants have been used up, or the reaction is no longer favorable to continue in the indicated direction. So in order to actually be spontaneous, we have to have a balance between two different factors. They sound very similar, but they are very different. The two terms are enthalpy and entropy. And the one we've used before and talked about before was enthalpy. And this one we've talked about has to do with heat. When we did potential energy diagrams, we talked about this value being delta H, the enthalpy or heat involved in a reaction. Entropy, this one's new. This one we're going to learn about today. But in conjunction with enthalpy, both of those two factors are going to help us figure out if a reaction will be spontaneous or not. So first we'll start with enthalpy. Enthalpy is the heat content of the system. Remember, heat is energy. It's internal energy, having to do with the motion of molecules. Nature is going to favor reactions that undergo a decrease in enthalpy or a decrease in heat. Now we know those as exothermic reactions, a decrease in enthalpy. A reaction that starts with a higher heat value, remember PE we measure on our Y, this is our reaction down here. Exothermic reactions start with a higher heat value in the reactants and end in a lower value as their products. So we have lower PE here. This is favorable for nature. For a reaction to proceed and release heat into the surroundings, we have a stable or more stable product in an exothermic reaction than in an endothermic reaction. So there's a direct relationship between potential energy and kinetic energy. So by decreasing potential energy, we also decrease kinetic energy. So going to a lower potential energy means that our molecules, our motion of our molecules, the heat contained in the molecules and bonds of matter, that's going to decrease. They're going to be moving slower. There's less energy stored, and molecules are going to be moving slower, less kinetic energy, less energy of motion. So since nature favors reactions that have a net decrease in potential energy, any reaction that gives off heat is favored. So exothermic reactions are going to be favored by nature. So enthalpy we know is the heat content of the system. And we've been using table I to look at different reactions that are exo and endothermic and their associated heat values. And on the bottom you're given a little note there that says any negative delta H value is an exothermic reaction, and therefore it's going to be favored. So anything on table I that's negative, there's a negative delta H, it's going to be an exothermic reaction and therefore will be favored. If it's a positive value, it's going to indicate an endothermic reaction and therefore it is not favored, because that reaction requires an net input of energy to continue to happen, and nature doesn't have an endless supply of energy. So endothermic reactions are generally not favored. Here's a nice easy example. Once you strike a match, the match will continue to burn on its own without doing anything else. Because that reaction, which is certainly exothermic, it's giving off heat, light, that exothermic reaction is favored because the products, the burned match and ash and smoke, is a more stable product than the combustible match before you lit it. But that reaction, that fire continues to burn without doing anything else. You don't have to keep turning something or causing friction or rubbing things together. It'll just happen on its own. Therefore, that is spontaneous. Now, to really determine if a reaction is spontaneous or not, we have to look at another factor called entropy. And entropy is a measure of randomness or disorder of the system. And this is what I like to refer to it as randomness. It is chaos, disorder. How disordered are things in a reaction, in an environment? That's how we can determine what entropy is. And nature is going to favor a reaction that undergoes an increase in entropy, or a reaction that gets more random or more disordered or more chaotic. So spontaneous reactions are going to be ones that lead to more disorder. And nature is going to favor those reactions. So if you think about not putting any energy into cleaning your room will continue to get messier and messier, more and more disordered, more and more chaotic. And nature favors that. Just don't tell your parents that. Entropy. So if we consider entropy with phases of matter, we have an increase in entropy as temperature increases. And as we increase temperature, our phases of matter will shift from solid to liquid to gas, so an increase in temperature by adding energy. So endothermic reactions to melt and to vaporize between phases of matter are an increase in randomness, an increase in chaos, an increase in disorder. Solids are very neatly lined up, right next to each other, all in a nice neat little row. Liquids getting more disordered. They're still touching each other, but they can move around each other. They're not quite as ordered. The gas is completely disordered. There's no order there. They're all over the place, never staying in one spot, never staying next to their neighbor. So gas has the greatest entropy or the most disorder. And solid has the least entropy. So that's the least disordered. This could also be considered the most ordered and the least ordered. But to put it simply, nature is going to favor an increase in phase. So nature favors the formation of gas versus the formation of solid because it's going to require not necessarily more energy, but it's not going to be favorable to try and keep all the particles of a solid together in a solid. At this point, you should be able to define entropy, which is the disorder or randomness of a system. Now, to figure out if a reaction is considered favored or spontaneous, we have to look at the phases to start with. If we have an increase in phase, and just to be certain here, an increase in phase is from a solid to a liquid to a gas. Then it's going to be favored. So with this reaction here, we have two reactants, one solid, one gas, and it forms a gaseous product. This would be considered an increase in phase because we start with a reactant that's a solid and a gas. We only end up with one that's a gas. We got rid of the solid. So overall, our only product here is a gas, which is more disordered than the two reactants, one being a solid that we started with. So this is an increase in disorder or an increase in entropy, and just based off of entropy, this reaction would be favored. Another example, we have solid aluminum reacting with gaseous oxygen, and it forms a solid product. So we start with a solid and a gas. We end up with only a solid. So we've now taken this gas, slowed down all of the oxygen gas molecules, combined them with aluminum, and have now slowed them down and ordered them with aluminum into a solid form. This takes a lot of energy to do that. And we're trying to order something which doesn't want to be ordered in a solid. So this is a decrease in phase. We're getting more ordered since we're only in a solid now, becoming less random. This is a decrease in entropy and is therefore not favored. This is just looking at phases. So we're going to have to combine both of these together, enthalpy and entropy, because those are going to work together to determine if the reaction will be considered spontaneous or not. Now, for the reaction to be spontaneous, nature has to favor the factors. If nature is going to favor the enthalpy and the entropy, so both of these are going to be favored, the reaction is going to be spontaneous. Nature is always going to favor an exothermic reaction that will increase in phase. So we're going to have negative delta H values that are gases. If nature does not favor enthalpy nor entropy, the action will not be spontaneous. Nature doesn't like or doesn't favor endothermic reactions that decrease in phase. So it doesn't favor endothermic reactions that are becoming solids or liquids. That is not favorable in nature. Now we can use table I to determine this. We can look at the phases of matter between reactants and products. And we can also look at the delta H values. So if both enthalpy and entropy are favored, the reaction is considered spontaneous at all temperatures. For this reaction, the enthalpy has a negative value, a negative 84 kilojoule per mole heat of reaction. So therefore it's exothermic and therefore it has to be favored, just based off of the enthalpy. As far as the entropy, well, we have a solid and a gas, and our product ends up as all gas. So this is an increase in phase and therefore is favored. We're getting more disorder here, more random. Because we've taken this solid carbon, spread out those atoms, combined them with hydrogen gas, and now these carbons, instead of being ordered next to each other, are combined with another element and in the gas phase. So this increase in phase means that due to the entropy, the reaction will be favored. Since both of these factors are favored, enthalpy and entropy, the reaction is going to be spontaneous at all temperatures. This is going to be the main thing that's going to change, is temperature. So both factors are favored, reaction is spontaneous at all temperatures. Now if both are not favored, the reaction is going to be spontaneous, will be non-spontaneous at all temperatures. So it doesn't matter if it's hot or cold, if both the heat and the randomness of the reaction are not favored, the reaction is going to be not spontaneous. Only adding energy is going to make it occur. So in this reaction, we look at the heat value first. It's a positive value, therefore it's endothermic, and any endothermic reaction is not going to be favored as far as the enthalpy. As far as the entropy goes, we have a gas and a gas and a gas. Well, they're all the same phase, but if we look at the moles, we have 1 mole of N2 gas and 2 moles of O2 gas for a total of 3 moles as reactants and 2 moles as a product. So since we have less gas flying around, 3 moles compared to 2 moles, this is considered a decrease in entropy. This is becoming more ordered due to less gas molecules flying around. So since we don't see a change in phase, we have to look at the number of moles. And since we have less moles on our product side and more moles on our reactant side, this is considered a decrease in entropy because we are getting less random. So since both of these factors, the enthalpy being a positive delta H and the entropy getting more ordered, both of these factors are unfavored, and this reaction is going to be non-spontaneous at all temperatures. So that's with both factors being unfavored. Now, what if one is favored and the other is not? Well, it's going to take a little bit of memorizing, so do your best to commit the following to memory. If the enthalpy is favored, so a negative delta H, exothermic reaction, but entropy is unfavored, then the reaction is going to be spontaneous only at low temperatures. Above a certain temperature, the reaction is going to stop. And that's due to the excess energy available at higher temperatures. And this negative value, the delta H, should help to remind you that it's at low temperatures. So enthalpy is favored, entropy is unfavored. At low temperatures, the reaction is going to be spontaneous. Now the opposite is going to hold true if the enthalpy is unfavored. If we have a positive delta H, but the entropy is favored, then the reaction is going to be spontaneous at high temperatures. And we'll use the positive sign of the enthalpy factor, the delta H, to remind us that it's at high temperatures. So this is when we have a 1-in-1 factor. Enthalpy being favored or unfavored, and entropy corresponding. We have to look at the enthalpy value, determine if it's endo or exothermic, and use that to decide at what temperature will the reaction be spontaneous or not spontaneous. That's about as hard as these are going to get. So we'll do a couple examples here. Looking at this reaction, we'll start with enthalpy. Reaction has a negative delta H, so therefore it's exothermic and is favored. Looking at entropy, we have a gas, and a gas. We have no change in phase, but we have 3 moles of gas on this side and 2 moles of gas on this side. So we have less gas flying around. So our product side is more ordered or less random. Therefore, it's a decrease in entropy and is unfavored. So, entropy and enthalpy. The entropy here is unfavored and the enthalpy is favored. So what we're going to remember here is that since the enthalpy is favored and entropy is not, that negative sign is going to tell us that this reaction is spontaneous only at low temperatures. So if we keep the temperature low of this reaction, it will occur spontaneously. For the next one, we'll look at the enthalpy first. We see we have a positive delta H value, so this reaction requires a net input of almost 26 kilojoules per mole to occur. So therefore this is not favored because it is endothermic. Looking at the entropy, We start with one solid reactant that ends up as an aqueous products. In the aqueous solution, that ammonium and nitrate ions are free to move around. So therefore, these are less ordered. These are more random. Therefore, it's an increase in entropy and is therefore favored. So here we have enthalpy being unfavored and entropy being favored. And since enthalpy is unfavored, we look at the positive value there. It tells us that this reaction is going to be spontaneous only at high temperatures. At this point, you should be able to explain that systems in nature spontaneously undergo changes toward lower energy and higher entropy. If you guys have any questions on this, make sure you write them down and save them and bring them up during class. Have a wonderful day, everyone.